In this video, we're going to discuss Gauss's law for electric fields. So this is actually one of Maxwell's equations, and Maxwell's equations are the equations that govern electromagnetism. So electromagnetism is described by Maxwell's equations. And all you actually need is Maxwell's equations and also the Lorentz force law, and that gives you all of classical electrodynamics. So in this video, we're going to focus on just Gauss's law for electric fields. And there's usually two forms that Maxwell's equations are represented in. There is the integral form and the differential form. So up over here, we have the integral form for Gauss's law. This is Gauss's law for electric fields, not Gauss's law for magnetic fields. Those are two of Maxwell's equations. What we're actually going to do in a second is convert Gauss's law in integral form to Gauss's law in differential form. And there's actually advantages to putting it into differential form, and there's also advantages to keeping it in integral form. Integral form tends to be introduced first because it's a little bit easier to understand mathematically, and then differential form is introduced a bit later, and differential form is more useful for doing theoretical manipulations of Maxwell's equations, and it's also more useful for looking at just a single point, right? Because this is an integral over a surface. It's a surface integral. So that's what S over here is represented. This is a closed surface. Now, what is the notation in this equation over here? Let's have a look at some of the notation. So we can see that E and S are vector quantities, and there's a dot product occurring here. So we're taking the dot product of two vector quantities. So it's E dot ds. And then we're taking that dot product and we're summing it up over an entire closed surface. And this little ring or this little extended circle, little ellipse, is to indicate that this is a closed surface. And the two integrals are there to indicate that it's a two-dimensional surface. Right? It's a two-dimensional surface, but it exists in 3D space. So it's a closed surface, and it encloses a volume. So when we convert from integral form to differential form, what we're actually going to need is the divergence theorem. Now, this is actually sometimes called Gauss's theorem. It's the same guy. It's the same mathematician Gauss. So it links together this quantity called divergence to the surface integral. So what this is saying is, we'll go through an intuitive explanation in a second, but what this is saying in terms of the notation, it's saying if you take the volume integral of the divergence over some volume V, then that's actually equivalent to taking the surface integral over some surface S. And this S isn't just any surface, it's the surface that encloses the volume V. And there are some variations on the notation, but I've chosen to use the triple and double integral notation here. Notice that there's no little ring over here because we're not doing a closed integral. We're doing just a volume integral. It's a triple integral. When you do a volume integral, you can parameterize the integrand in terms of x, y, and z. That's Cartesian coordinates. You could put it into cylindrical coordinates as well, or spherical coordinates. If you were to put it into cylindrical coordinates, you would have a z coordinate, which would be a vertical axis. Then you would also have the distance from the vertical axis, which would be your radius. And you would also have an angle, theta, around. So those are the three values you would need in cylindrical coordinates. In spherical coordinates, you would have one radial distance from a center, from that center point, and you would have two angles. In any way you parameterize a volume is going to require three parameters because it's a three-dimensional space. Any way you parameterize a surface, that's going to have two parameters. So you need two parameters to parameterize a 2D surface. Even though that surface is in three-dimensional space, it's a flat surface. It's like if you take a balloon around the volume. So imagine this as a simple example. You'd have a balloon. All the air inside the balloon, that's taking up the volume. And the balloon, the membrane of the balloon, that is actually the surface S. Another notation you might also see is instead of S, you might see a little funny shaped D and then V. So you could also see this. This indicates that the S surface, the surface S, is the boundary of the volume. So S is always the boundary of the volume. It's not just any random surface. It has to be specifically the surface that encloses the volume. And the surface can't be open. It can't have a hole in it. So in the example of the balloon we talked about, the balloon actually has a little opening, but it's sealed off. If you open that side of the balloon and you let the air out, it's no longer a closed surface. So you can think of it as popping the balloon, and the divergence theorem doesn't even work anymore. So we're going to use the divergence theorem along with some other definitions, and we're going to turn this into the differential form of Gauss's law. So let's go ahead and do that, and then we'll have a look at some intuitive examples as to what Gauss's law is actually saying. So first of all, let's recognize that here we have a surface integral of the electric field over some closed surface S. And that's equivalent to Q, which is the charge enclosed, divided by epsilon sub 0, or epsilon naught. Now, epsilon naught is a constant. It's the permittivity of free space. And Q is the sum of all the charges. And if you think about it, all of these charges can actually be thought of as an integral, right? You could be doing an integral for the volume. So what is Q actually? I'll write it over here in slightly smaller. Actually, I'll squeeze it in here. So we can say Q is actually equal to the volume integral. So I'm going to write 3 of these guys because it's a 3-dimensional integral over the volume V of rho dV. So what's rho? Rho is a Greek letter that denotes the density. It's the charge density. So it's not the mass density, but it is analogous to mass. So in the same way that if you've done some kind of dynamics or rigid bodies, you might have done moments of inertia and integrals with respect to volume of the mass density, and that would give you the total mass. If you integrate all of the density of some kind of chunk of material, you're going to get the total mass. And this is actually analogous to that example. So instead of taking mass, we're taking charge. This is the amount of charge per unit volume, right? How much charge is in each chunk of volume? So if you take a tiny little cube, you take the limit as that cube tends towards an infinitesimal small cube, that's what this density is describing. So this can be a function that depends on x, y, and z if you're in Cartesian coordinates, or on if you're in cylindrical or spherical coordinates, you're going to have the corresponding coordinates for that. But this is a 3-dimensional, it's a multivariate function. It depends on all the spatial coordinates. So this over here is another way to write the charge enclosed. If it's not a continuous distribution, if rather you just have several point charges, this is just going to turn into a sum. It's going to turn into a sum. I'll write that over here. It's going to turn into a sum, right, a big sigma, of all of the charges. And the charges are represented by little q's. So this I is just an index. So you can add up you can sum over all of these indices, and that's going to give you the sum of all the charges. Now that's actually the same as this over here. If you think about it, the units work out. If you're just adding things in units of charge, which are coulombs, that's the SI unit for charge, you're going to get coulombs. Coulombs plus coulombs plus coulombs, that's coulombs. Over here, what do you have? You have coulombs per meter cubed, or charge per length cubed. And then you're timesing by length cubed, because when you do the integral over 3 spatial dimensions, you have length cubed. So the length cubed and the per length cubed cancel out, and you're just left with coulombs. So you have coulombs on this side, coulombs on this side. So the units actually work out. But you might realize that coulombs, that's not the unit of flux. Right? This surface integral is actually flux. It's electric flux. How is the electric field going through a surface? So how do we reconcile with that? Well, what do we need to do? We need to divide by a constant. And that's what this constant is here to do. It's to give us the same units that we have on that side. It's also to scale this value and make the two sides equivalent. Okay, so now we have a representation of charge, and we also have the divergence theorem, which is sometimes called Gauss's theorem. So let's take these guys together and combine them to try and get an expression that just has divergence. Divergence equal to something. So the divergence specifically of the electric field. So what can we do on the left-hand side? We'll have a look. What is over here? See, the way I've written it over here is just some general vector field F, but we can think of this as specifically the electric field, right? So the electric field, the vector field that describes the electric field, we can think of that as this guy. So we know the surface integral over the boundary surface is equal to the volume integral of the divergence of that vector field. So let's go ahead and replace this surface integral with a volume integral of the divergence. Let's do that. So what we can do is we can write, I'll do it over here. So I'm going to write a volume integral of, I'll put it in brackets, the divergence of the electric field. I need a dV, and that's equal to, that's actually going to be equal to this guy, which is the volume integral. So I write 1 over epsilon naught, I'll keep that outside, and then I'll do the volume integral over V of rho dV. Now I'll keep this stuff up here, right? So that's our just a little note on the side as to what charge is equivalent to. So what do we have? We have a volume integral of the divergence that's equivalent to 1 over this constant, the permeativity of free space, multiplied by the volume integral of the density. Now, what can we do with this? Well, we can do some little manipulations. So just before we continue with the manipulations, I want to make sure that we're clear with what we've done over here. What we've done is we've used the divergence theorem to convert this surface integral into a volume integral of the divergence. And then we've set that equal to a volume integral of the charge density. That's what this is. This is a triple integral over the volume. And one little note on the notation, I have chosen to just write this del operator, something that's called nabla, the del operator. Some people like to write an arrow over the top to say it's a vector quantity, because it acts like a vector, because you can take dot products with it. But I've chosen to omit that because I don't want to have too many arrows and it gets a bit too clunky. There's no ambiguity. Everyone knows this is the del operator, and there's no other scalar quantity we could confuse it with. But all the other vector quantities, like the electric field, I've chosen to write with a little arrow on top to indicate that it's a vector quantity. It's not a scalar. So this has 3 components. But this guy is a scalar. This is a scalar field. It's got a value at every point, but it hasn't got any direction. Density doesn't have a direction. The electric field does have a direction. All right, let's move on and manipulate this slightly. So what we can do is we can bring this constant inside. So I'll do that. And then what we can do is we can apply the property of linearity and bring everything inside the integral. So what we're going to have is a massive volume integral of the divergence of the electric field minus, so I'll move this onto that side, and I'll put this guy inside here. I'm going to have rho over epsilon naught, or epsilon sub 0. And then we're going to have dV, and that's just going to be equal to 0, right? Because I've moved this over here to that side, and I've taken this guy inside the integral. Now it's part of the integrand. It's being integrated, because this is just a constant. Now, why can we do this? We can do this because of linearity. Integrals, they obey that condition. Now what do we have? We have the volume integral of some quantity is equal to 0. Now this actually implies that the quantity inside is 0. So we know that this is equal to 0 because the integrand is equal to 0. Now try and think about that intuitively. If you have a quantity which you're integrating over an entire volume, and when you've integrated it all, it equals 0, then that quantity needs to be equal to 0 as well. Now that's not very rigorous, but for our applications over here, we don't need that level of rigor. We just need to know if this entire integral is 0, this thing inside the integral, that also has to be 0. So let's go ahead and set this guy equal to 0. So I'll write that over here. We're going to have the divergence of the electric field is minus rho epsilon naught, that's equal to 0. Right? So that's this over here. And you can immediately see that we can just move this guy to the other side. And what's that going to give us? The divergence of the electric field is the rho, which is the density, the charge density, over epsilon naught. So it does have a similar form to the version in the integral form. right? We're doing some kind of operation to the electric field, and that is related to how much charge there is there. But this is talking about how much charge is enclosed within a surface. Whereas this over here, this is talking about at one point. The divergence at one point is proportional to how much density of charge there is at that point. So that's what this guy is saying, and this guy is actually saying the equivalent thing. So these two guys are the equivalent expression. They are the same law. They're just expressed in terms of different quantities and different operations. So in this guy is actually more useful for computing something that's happening at a single point, and this guy is more useful for computing something that's happening over a big chunk of charge or a big chunk of points. So if you have some kind of distribution, this charge distribution, then you're going to use the integral form, and you might actually use, so I'll write this below, you could actually use a slight variation of the integral form. You could do this. So I'll write this down. We have the electric field is equal to 1 over epsilon naught, and then we have this volume integral. So I could have actually written that up here when we were setting these guys equal to it, but my goal was actually to convert this integral into this guy. So I'll write this in full down here. So what do we have? We have this guy. And I'll also put a box around this guy because both of these guys are actually the same thing. They're equivalent, right? This guy is the integral expression of Gauss's law, and this guy is the differential way to express that. So these are two different representations of the same underlying physical law. And this is the basis of all of electrostatics. So if there's no moving charges, all you really need is this law. Coulomb's law for electrostatics, you can actually derive that from this. You can just take a point charge and then take another charge and think about what is the electric field due to a point charge, and you're going to get a 1 over r squared relation, the inverse square relationship. So why would we even bother converting between these two forms? Well, I've said that the integral form and the differential form have different applications, and they both have advantages and disadvantages. If you have some kind of blob, like I've drawn over here, if you have some kind of blob and there's various amounts of charge distributed in that blob, which form would be more convenient to use? Well, if you were just interested in the blob, you'd want to use the integral form. What you want to do is you want to find the total charge that's enclosed in that volume, and then you'd want to have a look at the surface integral. So the surface integral of the electric field is going to be directly related to the volume integral of the charge density. That's what this guy over here is saying. But why do we state this form instead of writing all of this stuff out? Well, it's because writing a little q, that q implies that it's just all the charge enclosed. So we don't have to worry about doing a triple integral immediately unless there is a continuous charge distribution. If you have a line of charge or a surface or any kind of three-dimensional volume where charge is distributed, then you absolutely have to compute this. But if you don't actually have a continuous charge distribution and it's just a discrete charge distribution, so just 1 point charge, another point charge, another point charge enclosed in some surface, then you're going to use this guy, which we've discussed, the sum of the discrete point charges. And if you take the limit of this, it actually gives you this, right? If you take the limit of these guys, you get that. Because the amount of charge in each little chunk in a continuous charge distribution, like this little blob, that is actually just the density in that point times delta V. Or you can think of it as, I'll write it up here, you can think of it as the sum of the density at every point times delta V. And if we take the limit as that delta V goes to 0, what's going to happen? Well, it's going to turn into an integral. That's what an integral is. An integral is the limit as these little delta V's go to 0. And that's going to be a volume integral specifically. And it's going to be, you can think of a delta V as delta x times delta y times delta z. It's a three-dimensional integral. So that's what we have over here. Now, I'm pretty happy with this little conversion that we've done. Now let's have a look at some intuitive explanations of what this law actually means. So we've got two different representations. We've got the representation in the integral form and the representation in the differential form. And we're going to take a look at both of them in the application to this thing. So this little diagram, to simplify it, I've just drawn a kind of 2D representation. But keep in mind, this is valid in 3 dimensions. And you're pretty much always going to be using it in 3 dimensions, because we live in a 3-dimensional universe, not a 2-dimensional universe. So in red over here, I have some kind of clump of material that has a charge distribution. It's a continuous charge distribution. But I've drawn these little dots to indicate that there's more charge in this chunk and less charge in that chunk. So we can describe all the charge distribution by some function, rho of x, y, and z. Right? That's the charge density in that little chunk. And what can we do? Well, we can say that if we draw an imaginary surface around this chunk, we can call that surface S, or the boundary of the volume. And we can take all of this volume over here, and most of it's actually going to be empty. Most of it is not going to contain the surface, or is not going to contain the clump. But what we can do is we can use this description, this kind of imaginary surface that just exists in our head. It's just an idea. And we can use that and then apply these laws, these representations of the physical law of Gauss's law. So let's do that. So if we were to do that, what we'd need to do is we'd have to calculate the volume integral of this rho, the density function, and then we could set that equal to this, which is the surface integral of the electric field. So the electric field is a vector field. So at every point in space, there's going to be a vector value that points somewhere. But we're only concerned with the surface. So if you imagine every point in this surface has an electric field vector sticking out, and it also has a normal vector. And a normal vector is the vector that is perpendicular to the surface. So what we're actually going to do when we compute one of these guys is you're going to take the dot product of the normal vector and the electric field vector. So if the closer they are in line with each other, the more, the larger the magnitude of that dot product is going to be, right? So that's what you get when you try and compute the surface integral. So just keep in mind that there's going to be electric field lines coming out of this. So you can represent that as field lines coming out. Like, for example, if a point charge would have field lines coming out, and field lines are representations of the electric field. Now, I have made a choice over here to say that the field lines are coming out, where the electric field is pointing away from that little chunk, little clump of charge. Why have I done that? I'm assuming that it's a positive charge. It's a net positive charge. Now, why can we do that? Well, it's just as reasonable to assume it could be negative as well. If it was negative, then you'd have things pointing into the surface. So if this bit had a net negative charge, you'd have electric field lines going in. And that's common in realistic systems where there's charge moving around. You're going to have electric field lines flowing out of positive regions and into negative regions where there's more negative charge. So you can see that this is a really good way to apply the integral form of Gauss's law. But what about the differential form? What about this divergence thing here? So what you can do is you can pick a point in the middle, and you can say, what's the value of rho inside there? And that's going to give you the divergence. So you can find the divergence of the electric field just by knowing the density. Or if you know that the density is 0, let's say the density is 0 at this point over here, what we can do is we know that the divergence is equal to 0. So the divergence is actually equal to 0 at this point. And then depending on your coordinate system, you can actually make some simplifications, either based on symmetry or based on some other useful things about the coordinate system you're using, whether it's Cartesian, cylindrical, or spherical, and you can actually derive some expressions for the magnitude of the electric field. Now this clump example over here is a very general example, and it doesn't have any neat symmetries. But if you have a point charge, there's spherical symmetry. If you have a line of charge, there's cylindrical symmetry. And if you have a plane of charge, you're going to have a lot more symmetries. So this over here is a kind of intuitive explanation as to what Gauss's law is actually saying. And we haven't actually computed anything because this video is purely theoretical. It's just about the theory behind Gauss's law. So I'll give you a quick summary. What we've done is we've started with Gauss's law in integral form. That says that the surface integral of the electric field over some closed surface is equal to the charge that's enclosed by that surface over epsilon naught. So this is a statement in the integral representation. Then what we did is we used the integral representation of the charge enclosed by introducing this quantity called charge density, represented by rho. And we also used the divergence theorem, which is sometimes called Gauss's theorem. And we converted this integral form into the differential form. Now, how do we do that? We just made some few adjustments. We said, okay, this guy is equivalent to this guy, and this guy is equivalent to this guy. Then we did some little manipulations, and we realized through some little implications of a volume integral that you can just get this simple form. Now, it does look more simple, doesn't it? The differential form does look a little more simple. Even though it looks a bit like hieroglyphics with these upside-down triangles, it is a lot more simple to work with when you're doing theoretical manipulations of Maxwell's equations. So this was Gauss's law for electric fields in integral and differential form.